What happened to this? Okay, so let's. So sorry for the delay. Let's start with today's topics. So as I said, the goal is inference. So last time we just understood how graphs are related to joint distributions. This time we look at inferring things given a joint distribution. So you already have a joint distribution, which just means that you already know the parameters of the joint distribution, and you're just trying to find find quantities like expectations, find marginals, find conditional probabilities. Okay, and so that's the goal, and we look at sampling as one bucket of techniques, including Gibbs sampling. Other bucket of techniques includes belief propagation. So those are the two big topics for today. Okay. So yeah, I just said, last time we said we did representation. This time we're going to do inference, and next time we're going to do learning. And if you're wondering like what is the, in which application flow will I use these techniques, sampling is very useful if you're doing anything Bayesian. Okay, so most of the models you've seen probably in the courses are non-Bayesian, in the sense that things like SVM or random forest, there is no notion of prior distribution or a posterior distribution. Whereas if you look at the Bayesian linear regression example in the 2 lectures ago, those are Bayesian models. So you can actually compute the posterior distribution over your parameters given the evidence, given the data so far. Okay, so you're not saying there's one underlying ground truth model. You always have a belief that maybe the ground truth model, you have a uniform belief. Let's say a model can be anything at the beginning. You've seen some data, and from given the data, you are saying I have a posterior distribution over what the model could be. There's no one single model. Okay, so once you have this posterior distribution, you want to get, if you want to get make predictions, then you'll actually have to integrate with respect to the posterior, which is like taking an expectation. Okay, so that's like a very obvious example where you would need to do inference. Okay, so but there are other examples that we saw last time. I mean, just in terms of graphical models, we saw LDA for topic modeling, we saw CRFs, we saw hidden Markov models. So they're all techniques. In fact, hidden Markov models, the inference technique is a general version of that inference technique is what we're going to see today, which is called belief propagation. Okay, so if you have seen belief propagation, you can really do inference in many different. You can handle many different joint distributions. Okay. Anyway, so for that, we'll start with first few minutes on understanding what is a factor graph, and then a very simple concept called variable elimination, to do inference. So what is inference itself? So let's say we have a d-dimensional random vector, okay, x1 to xt, and if you have been given a distribution over these d-random variables, then inference is all about just computing functions of it. Okay, so things like the mode, which is like so generally this is like we also use the word likelihood for this, right? So you can find the value of the random variable which has the highest probability mass basically associated with it, or you can compute things like means. It's just a summation, right? Or you can find a marginal. So first of all, you need to sum over everything else. For example, in this case, x1 to xi minus 1 and xi plus 1 to xd. So so this summation will give you x probability of the marginal distribution of just xi, and then you're trying to find the max over that particular feature only. Okay, and then things like conditional probabilities. Okay, because all these can be reduced. So if you have conditional probabilities, it's just a summation over the joint distribution divided by another summation over joint distribution. Right? In fact, I guess the numerator there's no summation. In the denominator there's a summation. Right? So those are inference objectives. Is the notion of what is inference clear? I mean, it's not something different. Many of the tasks that you've done already are essentially inference tasks. So you can somehow you might not have used. So inference and learning are two words which are used, I guess, sometimes interchangeably, but sometimes learning corresponds to just learning the parameters of the distribution, and inference corresponds to making these computations given the distribution. Okay. So is the task of inference clear? Okay. So given that, we'll look at, as I said, two key techniques: belief propagation and sampling. And the first technique, and to warm ourselves up, we are going to look at a simple simple trick that we've already seen before, which is called variable elimination, okay, to compute marginals, for example. So before we get into the techniques, let's start with a common common representation for the joint distribution. Common in the sense that last time we looked at two different graph styles, right? Directed graphs and undirected graphs. So both encode certain metadata. This is conditional independence information, but the graphs are not sufficient for us to actually write the factorization of the joint distribution. By which I mean that if you have a graph like this, it could have, let's think of the undirected version. Then there's a clique of size 3, right? And there's also 3 cliques of size 2, right? So the factorization could be this or this, right? So we don't know a priori. By just looking at the graph, we cannot say which factorization it is, okay? And but this is useful information. If you know that the factorization is like this, then you can do a different type of, let's say you're computing the marginal distribution. So let's say you're trying to find P of A, okay? Then maybe you can do different types of summations, different type of integrations if you knew the factorization, which factorization it corresponds to, right? So so that's the ambiguity, and to get rid of that ambiguity, we define what are called factor graphs, and they have two types of nodes, okay? Circular nodes and square nodes, okay?
Can we deterministic about the factorization in case of directed graphs?
Yeah. So the directed graph factorization is given, yes. So it's this trick is not really useful for directed graphs. It's useful for undirected graphs. But so what I'm saying is, if you have been given a directed graph, you can get a factor representation easily, as you said, because you know the factorization xi given its parents, okay? In this case, you don't know, but the factor graph will you given this, you can go to a factor graph, and then you have the common thing for both from both, okay? So and the factor graph idea is very simple. So what it does is, given a graph, okay, and if you have been given the factorization, then all you have to do is put a square block and relate it to the factors related to the random variables related to that factor. So there's going to be one square block per factor. So in this case, it's a random variable, it's a joint distribution over 3 random variables, but it only has one factor, phi of A, B, C, remember, right? So since there's only one factor, I'm going to put a block, and I'm going to link it and then add an edge between that box to the 3 variables of interest, okay? So all I'm saying is there's not going to be, so the difference between these two is there's not going to be an edge between nodes anymore, nodes as in the random variables anymore. They're always going to be a square box between them, okay? It could be directly between them, or it could be like this, okay? So that's the idea of a factor graph. So let's see some more examples actually. So is this example clear? So from here to here, all I said is drop these edges, okay? And since there's only one factor here in this representation, I'm going to put a square. I don't have to label it, and then I'll connect the arguments of that factor with edges, okay? This is just a,
In the previous slide,
yeah.
The second case,
Yeah.
the second
Yeah.
case, the
Yeah.
graph will essentially look like a triangle with 3 square boxes between all the nodes.
Yes, good point. So yeah, we can, yeah, that's it. So there's going to be a box here, and there's going to be a box here. Good point. So is the question and the answer clear, everybody? Okay. So this is just so that we have a common understanding of what the graph represents, and then we'll directly jump into the methods to infer, right? So okay. And this, what I just said is, is told in a in textual manner here, and with the notion of factor graphs, we don't really have to think about directed and undirected graphs separately, okay? Although they have their own, the reason why we have undirected and undirected graphs is because sometimes some conditional independences can't be represented in one or the other, and we had some minimal examples, like 4 node examples from two lectures ago, which said, certain conditional independences can only be represented in one or the other, okay? So that's why there's 2 different graph models. But for inference, we can actually condense both of them to factor graphs, and then there's just a factor graph, and then we can directly do inference on that, okay? Um, so as she pointed out, for example, if you have a undirected graph like this, then you could have a, depending on how the factorization looks like, you could have either this or this. So these are just the same examples, but with one additional node, so 4 node example, right? So that's fine. So given the factor graph, you can actually read what the joint distribution is. Just like how we went from a factorization to a factor graph, we can go back. So for example, here you can see that x1 and x2 are connected to two factors, right? fa and fb, and x2 and x3 are connected to one factor, and x3 only has one factor, right? So you can write the product between these factors, and that would be the distribution with some normalization. So 1 by z is always a normalization that we add, because these factors, the terms, they don't have to be numbers between 0 to 1, unlike a directed graph. Okay. So here we're using f's as f's to denote factors. We have used phi's before in the previous couple of slides, but it's just same notation. Okay. So is this clear for this graph? So here you may have a confusion that there are two factors, fa and fb, which both connect to x1 and x2. So there seems to be some redundancy. That is true for this example. Well, that's okay. I mean, you could have a function which is a product of two functions with the same arguments, right? So yeah, so this is the factor representation of this joint distribution between the 3 random variables. So the 3 random variables, they don't have an edge between them. Okay. So let's see. So now this is I've used f notation for a directed graph actually. So here p of x1, x2, x3. I've used fc of x3 given x1 and x2, fa of x1 and fb of x2. Okay. So I could have used p, right? P of x3 given x1 comma x2, and then p of x1 and p of x2, right? So for this also you know how to draw the graph, right? So what would it be? So you have x1, x2, and x3, and all 3 of them have a factor, right? Square node, and there's a square node corresponding to this guy, and square node corresponding to this guy. Oh, actually, yeah, it's fine. Let's call this x2, x1, and x3. Right? Any questions about this? Okay. Okay, so I mean, what I just wrote in the previous slide is the same thing. Okay. Okay. And as he pointed out, for directed probabilistic graphical models, you don't really care about. I mean, you already know the factorization, so you can add boxes like this, but that's kind of easy. Okay. Okay. So now let's do the warm up. We'll do variable elimination, which is something that you already know. Is just we are reintroducing the name here. So which is as follows, right? So if you have let's say you have a joint distribution P of A, B, and C, and you want to find P of A, then you have to sum over B comma C pairs, all the other pairs of values that B and C random variables take of P of A, B, and C, and same thing with integration, right? So if you do this, then you'll get the P of A, right? Variable elimination is just saying that okay, don't do the summation simultaneously, do it in a clever way, okay? And so let's say this is the example factor graph representation of our 4 random variables, A, B, C, and D. Okay, so D is the one without has a f of D, and you know that everything else has a pair relationship, pair factor, which is this. So let's say in this example we want to find P of A comma B. Okay, so so we are marginalizing out random variable C and random variable D, right? Okay, so first we do this is just a warm up. So let's do marginalize out D. Okay, let's marginalize out D. So we get the joint distribution between A, B, and C, and if you write it and you use the factored version, so you can push the summation of d inside, right? You don't have to really multiply all of them together and then sum over the rows which include d, okay, right? So I push the summation inside because if the first two factors don't involve d, and then the summation over d, I'm going to call it, I'm going to use the representation mu of d to c of c, okay. What is this notation? This is just a mu is just a place in, I mean, I could have used some other like symbol. Mu is just a function, think of it as a function whose argument is c. Why is it c? Because c is the only guy left if I sum over, so just focus on this underlined thing, right? C is the only guy left when if I sum over d's. If there was something else, let's say e or something, then it would be a c comma e, okay. And the first argument just saying that is the thing I am kind of summing over, okay. And the subscript and this is kind of redundant, but it's the same, okay. So we have to compute this underlined part for every c value, okay. If we can compute this underlined part for every c value, then we can drop that. So basically we can drop this underlined part and just use this function, and that's our factorization for the joint distribution between a comma b comma c, right? Is that clear? Okay, I may be going slow, but let's do it slowly. And then our objective is to find the joint distribution between a and b. So again we sum over c, which is the thing that we don't want. We marginalize it out, and so that again you can push the summation inside because one of the factors doesn't involve c, and we'll call that vector. So that function mu subscript c to b of b, because b is the only guy left, okay, and we have to compute this for every b value, okay. So why am I bringing additional notation is to kind of I guess this is just a precursor, and these are going to be called messages in a subsequent algorithm that we'll look at, belief propagation, okay. So these are just vectors. So just think of a, b and c are just discrete random variables, okay. They're only taking finite values for simplicity, and there are some intermediate computations that we have to do to get to that marginal distribution between a and b only. And those intermediate computations, we are going to store them as vectors. Essentially, if all these are discrete, then mu of that mu thing, the circle, both the circled ones are just going to be vectors, okay. In this case, okay, for every c value there's going to be one number, so it's a vector, and you're going to call that vector a message, okay, eventually. But for now, that's the reason why I introduced this notation, okay. So any questions about variable elimination? So what happened? What is variable elimination? It's just saying that if you have a joint distribution between 4 random variables, then you would have a, b, c, d, and some number, right? I mean the number column would have numbers which are between 0 to 1, right? This is the probability table. For every value of a, b, c, and d, there is some number, right? Now if you want to marginalize out, you would pick, okay, look at all the rows where c is some value, d is some value, and average it out, right? Actually, it's not the right way. So pick values of a and b and average out all the, pick values where a and b are taking 2 values, and there will be multiple rows corresponding to the same values of a and b. Just sum them out. You could do that, okay. That's a graphical, that's a intuitive way to think about it, and computationally this is what you should do, okay. Is that clear? So how many of you are not familiar with this table representation for a joint distribution for discrete random variables? So probability tables, CPTs, I don't know what they're called, but I think they're called CPTs. So let's see. Yes. No, I'm just saying that if you have a, say, P, so D. So all I'm saying is if let's say A, B, C, and D are binary random variables, then A and B taking a value 0 and 0, there'll be many C values, right? So it's going to be 0, 0, 0, 1, 1, 0, and 1, 1. So you would add all these numbers up to get probability of A is equal to 0 and B is equal to 0. Okay, that is a naive way of thinking about it. And the variable elimination thing was just saying that, okay, if you're going to do that, then you don't have to you can do that summation by looking at the table, but we already know that probability of A, B, C, and D actually are factored. So there is some factor 1, factor 2, factor 3, and factor 4, right? Remember that example had 4 factors, has these 4 factors. So if you have 4 factors, you are actually not going to store this huge table. Okay, you're actually going to just store the factor specific tables. Okay, each factor is a function of two inputs, right? So f1 is just a function of 2 things. Okay, f1 is a function of 2 things, f2 is a function of 2 things, f3 is a function of 2 things, and f4 is a function of 1. Okay, which means that if you have so let's say I said A, B, C, and D are binary, which means that f1 is just going to be will have 4 rows. Okay, which is the 2 values of A, the value of A and B, 0, 0, 0, 1, 1, 0, 1, 1, and similarly f2 will be similar, f3 will be similar, and f4 will be 2 values. Okay, and if you have 4 tables instead of the full 1 table, then the question is how do you compute this marginal how do you compute P of A comma B? That's all. There's a difference between representation, because so what is the difference between this table, let's say A, and this set of tables B? Is the factorization. So you can use the numbers in the second set of tables to get the first table, right? But the first table doesn't tell you the details of that things can factorize. The second table is the one, and in fact the number of numbers here could be smaller than the number of numbers here. So for example, here the number of numbers will be 2 to the power 4. Here maybe it's similar because this is a small dimensional example. Let's say 4 plus 4 plus 4 plus 2. Okay, 14 numbers, right? 14 versus 16, let's say. So the number of numbers decreased because you had factorization. Is that point clear? It's a tangential point I'm making, but is that point clear? Okay. So by factorization or by having metadata, you are actually reducing the number of numbers needed to represent the distribution. Okay. But anyway, so any questions? Okay, coming back to variable elimination. Variable elimination is just about pushing the summations properly inside, and that is kind of obvious. You did not even have to give a name for this. If you knew the factorization, you would push the summations to appropriate appropriate levels and then just do the summation. That's variable elimination. Push it to the right level and then sum it over, and that's the eliminating that variable. In this case, we eliminated D first and then C next to get the marginal. Okay, that's the warm up. Any questions? Okay, so let's go to belief propagation. So what belief propagation does is it generalizes the idea of variable elimination, and one of the popular applications of belief propagation, it used to be, I guess now everything is mostly deep learning, used to be image segmentation. So what is the image segmentation task? So you have an image and you need to label every pixel. Okay, so you need to label every pixel according to belonging to some class. For example, the simplest labeling task could be foreground versus background, but there could also be other tasks like is this patch grass, is this patch wall, is this patch the road, things like that. Okay, so you could use so people used to use, you can actually use belief propagation to label the pixels of a image. Okay, and what is going to exploit? It's going to exploit some spatial relationship where each pixel is going to be a random variable, and so there's going to be some relation between that random variable and the neighboring pixels, and so some sort of edges between them, and so you will have a particular factor graph corresponding to that task, and then you will do inference on that task. Okay. Anyway, so let's see. BP is a generalization of variable elimination. It's also called sum product algorithm, and it turns out that when factor graphs are trees, okay, this is important. So we introduced the concept of trees and not trees before. When trees were basically there's only one path between two nodes, and there are multiple paths if it's not a tree. If factor graphs are essentially trees, then belief propagation will give you the correct answers. Okay, and variable elimination will also give you correct answers. to compute things like marginals and conditionals. Okay, so that's something that we will not. So we'll just accept it as a fact for now, and we'll look at pretty much factor graphs which look like trees. Okay. Yeah, you can actually use it for general graphs, which means that, by which I mean that there's a node here. If there's a factor, and a node like this, okay, then this is not something that we saw before, right? So in my previous examples, it was just something like a line. Yeah, this is pretty much it. And maybe there was previous examples where, yeah, mostly it was a tree. Okay, you can have a factor graph which is not a tree, right? So this is an example where there are two nodes, x1 and x2, and this is not a tree, right? So for trees, it turns out that inference using belief propagation may not work for non-trees. For trees, it's fine. Okay. So let's understand now what we're going to do in the next few slides and next few minutes is to understand the procedure of how belief propagation computes the marginal distribution. Okay. So for us, what we're going to do is use this as a running example. So this is a particular factor graph. It has 5 factors. Okay, too many, but not too many, but not too few, so that we'll understand all the nuances. So it has 5 factors and 5 random variables, so 5 nodes, and we can just see what the factors are. For example, f2 is connected to 3 random variables, right? And f3 is only connected to C, f5 is only connected to D, right? And f4 and f1 are connected to 2 random variables each, right? And let's say our task is to find the marginal probability of A comma B. Okay, so how do we compute the marginal probability of A comma B? For this graph, you can actually just you know these factors. If you want the marginal probability of A comma B, you can just do summation, right? You can just do summation over the other 3 random variables, right? C, D, and E. You can just do the summation. You can just push the summation inside, and you'll get the marginal probability of A comma B. Okay. For this graph, it's kind of obvious how to push the summations inside. But in general, if there are too many variables, let's say 100 variables, and it's not uncommon to have graphical models with hundreds of variables, then it's not clear which order the summations have to be pushed. Okay. For example, should I do the summation of E first push E summation over E in and do some computation, or should I do first D in and do some summation, or like which order should I sum first is not clear. Okay, that ordering issue will become critical when you have more and more random variables. Okay, so that's why variable elimination is being improved upon when you use belief propagation. Okay, so the 2 key concepts in belief propagation: the notion of messages and the notion of passing those messages. And just as a prelude, I said those vectors, right? So those vectors are going to be messages, and we'll see in detail soon. And we'll pass around those vectors across this graph. Okay, so there's going to be a very visual algorithm. So try to ask questions when you're not able to follow. Okay, so what are the 2 components? Messages and message passing. So what are messages? Messages are just functions, and for us it will just be vectors. You know, a function is a vector if you have input being a few discrete values, right? If all my random variables are taking discrete values, few values, let's say, then a function is just a vector, right? For every value, what is the function evaluation, right? And so messages are things which are passed from one node to another. Okay, so I have my original factor graph, which is in the black, and then I have a bunch of messages that I've kind of highlighted here. Some of them are named, right? So for example, mu C to F2, mu F3 to C, mu B to F1, mu something, F1 to A, and in this case F2 to B. So there are several messages being passed between nodes. Okay, so just think of it as there's really a store at each node, and it can receive messages. Think of it as it can receive a bunch of messages. In this case, vector representation of messages, like really literally telegrams or whatever, snail mail. and then it does give looks at the messages, computes something which is going to be a new message, and passes it on to other neighbors. Okay, that's essentially what's happening visually. Okay, so let's look at let's intuit like what could be the message, and it's going to be based on variable elimination concept itself. So let's see. So P of A comma B, we said we know the factorization, right? This is the factorization: f1, f2, f3, f4, and f5. Sorry. So we were supposed to sum over C, D, and E, right? So f1 doesn't involve C, D, or E. So f1 is just as it is. Okay, and this whole thing, okay, sum over C, D, and E, we're going to call it a message from the factor node f2 to B. Okay, so what I'm saying is only this part contains C, D, and E, right? The one circled, right? And the one circled and the ones not circled, they're connected by this. I think I eliminated it, but f2. That's f2 over there, right? So there's going to be a message which is going to be passed from this part of the graph, which is circled, to B in this case. Okay, B is going to receive a message from rest of the guys. Okay, that message is going to be a vector. Okay, what is that vector? That's a vector whose arguments are going to be B. Okay, mu to f2 to B, whose arguments are going to be B. So let's say B takes 3 values, then this message is going to be having 3 coordinates. Okay, once B gets this message, it can compute probability of A comma B. Okay, that is kind of obvious, right? So if I know what this message is, then for A comma B, the probability of A taking a value, A and B taking a value something, is just f1 of A times B times this number. Okay, whichever coordinate, whatever value I'm evaluating B for. Okay, is that clear? The first message that was being passed from f2 to B should be clear. Now we'll get into the details of other messages. Any questions? Okay, so that's the message. So f2 to B, right? Which was the above expression, underlined expression star here. Now that we are gonna, yeah.
So in case A and C are also connected
A and C are connected.
by one other factor.
A and C, oh, in case A and C were connected, yes, something like this, right?
So in that summation term, we have another factor f6 or something.
In that summation, yeah, there will be another. So
In that case,
okay, so let's answer one question at a time. So this is not a tree. Okay, so belief propagation will not work exactly, will not compute the exact marginals on this. I guess not that it will not, but it's not. We cannot prove that it'll get the right answer. Okay, it may get to the right answer for some reason, but yeah. So now your question is what?
so then I was asking, like, 2 messages will be passed. One message will be
Yes.
from this entire branch to B, and then the other will be
Yeah, from here to here. Yeah. So there'll be 2 messages. So basically, here I took an example where I want to marginalize and keep only 2 variables and everything else done, remove. So that's why, and since the relation between those 2 variables and the remaining variables are only connected through that factor f2, that's why I'm passing only 1 message. But if there was something like this, there will be another message here, like from the top. Let's say if there was a link between A and C, if there is a factor, then there would be a message from the top as well. But then there's a question of like what is scheduling and how to pass messages properly. We'll discuss it in detail. So let's wait for a couple of minutes before we discuss that. Yeah, you had a question?
No, I guess you said we'll discuss that later.
Yeah, how messages are passed. For trees, actually, it's going to be obvious because irrespective of where you start, it's fine. But for if it's connected like this example is something we need to discuss offline. Okay. Yeah. So now I'm dissecting the message that was sent to B. Okay, this the one on the left hand side here. So and we know, I mean, it's a function of 4 factors: f2, f3, f5, and f4. We can send the summation over E all the way to the end. Okay, the summation over E is sent all the way to the end. Okay, it will evaluate to something, right? I am not explicitly calling a message there here. Oh, okay. Yeah. So I'm defining I'm just defining few things here. So let's just focus on F3 for now. Okay, F3 of C. Just think of that as I don't know if I named this correctly, but yeah. So anyway, that's the same equation from the last slide. So let me explain this slide properly. So the message. Okay. So this square bracket here, okay, is a message from D to F2. Okay. So so think of this summation as a function of this. Once I sum this out, it's some function of D, right? Right. So some function of D, and there's an Fi of D, and from those two, I'm going to send a message to F2. Okay. And let's look at the graph actually. Where is D? So this is the D node here, right? It needs to get it's getting messages from two factors. Okay, that node is getting messages from two factors. Okay, F5, which is directly, there's F5 of D function there. That's why it's getting a message. Remember that function is just a vector, right? D is a discrete random variable. Let's say it's taking 10 values, so that's a vector. And then F4 of DE, I'm summing over E, and that's some G of D or whatever. Then that is also being passed to D. Okay, so the messages. So the message. Okay, so the message at D is going to be this guy and this guy. There are two vectors. Okay, the message that D itself passes on in this case is going to be the product. I mean, we are just looking at this equation. It's going to be the product of the two messages that came in. Okay, so that's the message that D is passing to F2. Okay, I think let's go back to the bigger zoomed in picture. So all I'm saying is there's a message being passed from F5. There's a message being passed from F4. Okay, those two messages, I'm just multiplying them together, and that's the message that is being passed to F2. Okay, so we are talking about mu of D to F2. Okay, so mu of D to F2. Okay, so what am I doing here actually? We know that for this particular graph, we know how to push the summations inside and look at factors anyway. This exercise in this example is just to name these summations as this and group these summations and products and call them messages. Okay, and then we'll formally talk about in general what is a message and what is being passed around. Okay, in this example, we are just looking at anyway. Even if we did not have the notion of messages, we would pass these summations around and do the summation. But now we are just calling them as messages by just grouping the terms together and calling them messages. Okay, so I'm just calling F5 times D times that summation over E of F4 of D comma E, that product, as a message that D will pass to F2. Okay, a message being passed from D to F2 will have an argument which is the node itself. I mean, which will be D values itself. So note that this message is different from the message that you saw previously. Okay, so the message from this is the message that we spent some time on, is a message from F2 to B. Okay, so that message, this message here, star, is a message from what is it called? A factor node to the node B, right? Whereas this message, okay, which we just discussed now, the second star, is a message from a variable node to a factor node. Okay, so it's slightly different, but we are just interpreting through this example what we could call messages, and I'll show you the general principle. And general principle is very simple, but let's walk through this example a little bit. Okay, so, and in this case F3, I'm just calling it as I'm just adding too much notation and calling F3 itself as a message from C to F2. Okay, so yeah, the message from C to F2 is the message is equal to F3 of C is what I'm defining it to be. Okay, why is the case? Think of what is the message I can get from, so for C, what is the message I can get is a message from F3. Okay, actually I can get message from even F2, but if I want to pass a message to F2, I'll get a message from F3 and I'll just pass it on because I don't have any product stuff to do. Okay.
So only the factor node can pass messages.
All nodes can pass messages. We saw one example. Where is this? In this example, in this page, we looked at a message, that underlined thing, star, again, double star here, is passing a message from a factor node to a variable node. Okay. So the circular ones, let's call it variables, just to repeat, and square ones, let's call it factor nodes. This message is from a factor node to a variable node, right? The double star one. And in this page, the square box is a message from a variable node to a factor node. Okay, it's D to F2. Okay, this is just an example. We'll get to the principle, and it's actually pretty simple. But okay, so the reason why I wanted to put these, loaded symbols is because then I can have a product like this. Okay, so the message that went from F2 to B, okay, to the left hand side, is a sum of the product of messages, sum of the product of a couple of messages that F2 itself got. So remember, there is a right hand side F2 here. It's the product of messages that F2 itself got. Product of those the two messages with its own factor function. Okay, that's this F2 function itself. Multiply that, and then sum over the variables that are irrelevant to be passed to the next guy. If I want to pass a message to B, and I'm a factor node, I should remove all the variables which are not related to B. In this case, F2 has C and D involved, right? So I need to remove them, as in sum it over. Okay, so that's the structure. So this is just an example of the decomposition of a message from F2 to B as a function of what messages it got. It got a couple of messages in these two things, and it multiplied those two messages with the local factor function, summed over variables which are irrelevant, and then passed the resultant vector, which is just a vector of B to B. Okay, so yeah, so I guess this is a message from factor to a variable. Yeah, so a little bit of notation in general. So this is what we saw, that there is a message that needs to be passed from F2 to B, is a product like this, product of bunch of incoming messages and the local factor. I'm going to use this general form for any factor to a variable it needs to pass on a message to, as first of all get messages. This product here is make a product of all the messages that I got from other variables. Okay, so product of all the variables, all the messages that I got from other variables, not involving the variable that I want to pass a message to. So if I want to pass a message to B, I don't need to get a message from B, from the other guys. Remember, let's look at this example. If I want, let's focus on F2. F2 wants to pass a message to B, right? It's getting messages from two other guys, C and D. Okay, so that's the product of. So this is general form. This product is what this part is. Okay, getting two messages, do element wise multiplication, and then this part is this phi. I'm using the phi function to represent the factor corresponding to that factor node, and then summation over D, C and D is the same as summing over all the nodes except the node you want to pass a message to. So if I'm passing a message to B, then I want to sum over C and D. If I want to pass a message to C, I want to sum over B and D. Okay, is that clear? So in this slide, what we did was just look at this. I mean, we discussed the structure in the previous slide. And in this slide, I just said from here we can just use a general notation where if I want to pass a message from a factor to a variable, get the messages from other variables. Okay, get the messages from the other variables, multiply them with the local factor function, sum over all the variables which are irrelevant to the guy I'm passing the message to, and then that's that operation. If you do, if you get a vector, and you pass it to the variable of interest. Okay, that's a message from a factor node to a variable node. Is that fine? Okay. Now, message from a variable to a factor node is a little bit easier. Okay, and for that we just saw in I think in the previous two slides there was a message from D to F2, right? So we are saying we want to send a message from this circled area to F2. Okay, and the way we're going to do it is we'll get a message from the other two factors that we're connected to. In this case, D is connected to three factors. F2 is the factor it wants to send a message to, and it has two other factors, F5 and F4, which are also connected to D. What it's going to do is it's going to get two messages from F5 and F4. It's just going to multiply them, and that's it. That's the message that will be passed to the the factor of interest. Okay. So in this case, get a message from F5, get a message from F4. These are vectors of length. Let's say D is taking 4 values, then these are vectors of length 4. Do an element-wise multiplication. That's going to be a vector of length 4, and just pass it off as a message to the factor F2. Okay. So for a variable node to pass messages, it's easy. Whatever messages came in, just multiply them element-wise and pass it forward. Okay. Whereas the factor node message, from factor to a variable, it's a little bit two-step process where first you collect the messages you got, multiply them together, but you also have a factor corresponding to that factor node. So you multiply it with the factor node, average out the things which are irrelevant to the guy who I'm sending the messages to, and then send the message. Okay, so that's the general idea, and yeah, and that representation is like this. So if I want to send a message from X, from X to some factor F, then I need to look at all the neighbors of X. Okay, all the neighbors of X will be other factors. All the neighbors of X will be all factors, but all the neighbors except the factor I want to send the message to, factor node I want to send the message to, that is any of X minus F, basically. That's what it means. So get the messages from everybody, all other factors, multiply them together, pass it forward. Okay, that's the general form. So is the notation clear? Like it's a little bit messy, but it's a minimal notation needed to say who's sending the message to whom and what is its argument. Okay. Are the two pieces clear? Now, okay. So now but we already saw, for this example, we already saw what happens, right? So we just had to pass a message, not here, sorry. It's okay. Anyway. Yeah, not here, but here. So we just had to pass a message by somehow getting rid of all these variables, summing over all of them, and there was one message, one vector, which would multiply with the factor corresponding to a comma b to get me the marginal distribution, right? So remember, there was a p of a comma b was just the local factor f, I guess f1 of a comma b, and a message that I got from the rest of the graph, which is a function of b, right? That would be so that's what we wanted. So for that, we defined each one of them to be as a message between the factor node and a variable node. And what I'm going to do next is to say how these messages are passed. Okay, so we just said passing a message. We just described passing a message from a factor node to a variable node to factor node. But it's not. And I'm okay. At this point, we're just going to assume that passing of messages already happened when we did that computation of mu of b. So that, remember, the mu of b. This expression already had the summation of summations and products, right? So which means that first I was supposed to get a message. Then I would pass a message to b, right? But I was supposed to get two messages first. So those two messages I could have passed if by using this logic here, like this type of logic. So first I should have passed messages from somewhere to get to that f2, and then from f2 I can pass a message to b. Okay, so there was some order relationship here, but we'll discuss that pretty soon. So okay. Yeah. So let's say, I mean, so here is, it's not a different example, it's the same example. Now I'm saying I want to compute just P of A. Then P of A for that would be, I already have a, so I need to pass a message from B to F1, and then that would be the message, okay, and then F1 local factor would be a function like this, sum over all the irrelevant variables. That would be the message that F1 will pass to A, okay, and the message that was passed to A is the marginal probability of A, okay. So that's the, I guess, in terms of computation, what we want to interpret the messages as, okay. So is this so we saw P of A comma B before. Is P of A is just the next extension? Is that clear? Okay. Okay. So what is the algorithm? So we just talked about messages, and for the previous example we could have just done summation. There is no need for belief propagation. But for large graphs we have to get this idea through, just like d-separation versus the 3-node stuff that we saw 2 slides, 2 lectures ago. So there's going to be 3 parts to the algorithm. First part, and there's 3 parts. 2 parts we just saw through examples, which is variable node to factor node to variable node message structure. The third part is just initialization. So that will kind of tell us how to pass messages, like what is the sequence in which I'll pass messages. Okay. So 3 ingredients: initialization and the 2 types of messages that I'm going to pass. Okay. And this is going to be critical. So we'll first start with leaf nodes. Okay, it's a tree. We have a tree, so we'll start with leaf nodes, and we'll start with leaf nodes to define the first set of messages, the first message. Okay, because see, I mean, in the previous message passing, from variable to node, variable to factor node, or factor node to variable node, I said I will get messages from elsewhere, right? But where are those messages? There is a chicken and egg problem here. So that's why we'll start with leaf nodes. So leaf nodes means if the leaf node is just a factor node, then the message from the factor node to the variable that it's connected to is just going to be the factor value itself. I mean, it's the factor function itself. Okay. And if the leaf node is a variable and it needs to pass a message to the factor node, to a factor node it's connected to, then the message is just going to be identity message. Okay, so that's how you start. So because these nodes don't have anything else that will give a message to them. Okay, if they want to, like for example, if the graph structure has a part like this where there's f which is dangling and it's only connected to one variable, then it doesn't have an incoming message. So it just has to pass on its local function, which is the factor function, to the variable in this case. And in this case, the variable has nothing else connected to it. It just has one factor connected to it. It has to pass a message to that factor. It will just pass all ones. So if that variable is taking values, if the variable is 4-dimensional, then it's going to be a 4-dimensional vector with ones in each coordinate. Okay. So those are the initial. So once you've gotten the messages, incoming messages, then it's bootstrapped. Now you can pass messages forward and backward. Pass messages forward as needed. Okay. We're going to look at trees, so there's no need for, okay. Okay. First step, initialization. Start with parts where you only have dangling variable node or a dangling factor node. Next part, now the same expression that I had like 3 slides ago, but more in picture format. So the message from a variable to a factor is going to be all the other factors that it's connected to. Let's say F1, F2, and F3 in this case. It wants to send a message to a target factor F, then get the messages, okay, get the messages from these 3 guys, multiply them together, and pass it forward. Just a recap of this. Okay, is this clear? Okay. Now the message from a factor to a variable is the same thing. This is a factor. It's connected to a bunch of variables. It has a target variable for which it wants to send a message to, let's say. Then get the messages from the 3 variables it's connected to in this example, and I want to send a message to X. Then first multiply all the 3 messages. They are of the same dimension. Then multiply it with the local factor function. Okay. This function could be a function of, this function is actually a function of 4 variables actually, y1, y2, y3, and x in this case. You sum over all the variables that you you marginalize out all the variables that are irrelevant to the guy you are sending to. So you sum over y1, y2, y3 in this case, and then that's the message to the variable node. Okay. So why did I say a target? So the ambiguity now is that I said there's a target node that I want to send a message to. So why did I pick only x2 to send a message to? Why couldn't I pick y1 to be sending a message to, or y2 to send a message to, right? I could do that, right? Let's say I want to send a message to y2, then I'm supposed to collect messages from the other three guys, y1, x, and y3, multiply the messages that I got from them, local thing, forward it, right? So I could do anything. Like I have 4 configurations, 4 messages to pass from that factor to variables. Turns out, but as tree, if I start from the initialization, there's only one direction, so I will not have this ambiguity of choosing one direction or the other. Okay, because it's a tree, there's only one path from a node to a node, any pair of nodes. So that kind of alleviates this issue of which it'll come as naturally as which is the target variable node to send to, and what is the incoming nodes from which I'll get messages. Okay, so as I was just pointing out, messages depend on incoming messages. So what you do is you start from leaves to a designated root. So you have a tree factor graph. Pick any node to be a root node. Okay. If you don't know what the target is, so okay. If you want to compute p of a comma b, then there is a particular way in which you are supposed to pass messages. Okay. But let's look at a general construction, and I'll comment on p of a comma b, which we saw previously. Okay. So first thing, start from leaf nodes. Given the tree, pick any node to be a root node. Start from leaf nodes and start passing messages. So for the leaf nodes, you know how to pass a message. This is easy. And then pass messages forward till you hit the root node. Okay, pass messages till you hit the root node. In this case, x3 is the root node, arbitrarily chosen. So x3 is the root node. So I start passing messages from x4 and x1. In this case, it's easy to see that these are the 2 messages. There's no issue of circular logic here. And then at x2, you got 2 incoming messages. You know what the target is, so you send it forward like this, and here to there is also fine. Now, what you do is once you get the message to x3, you can again pass it back. You can pass back the message that you got to x3. You pass it back all the way to the root nodes, so all the way to the leaf nodes that you started with. Okay, so this is like pass messages forward to some designated root. In this case, I just picked x3 for simplicity, and then pass messages all the way back. Okay, if I had chosen x2 as a root node, then I would have gotten 3 messages from the 3 directions here. I would have gotten some final message here, and then I would pass that message back to all the 3 nodes. Okay.
Why are we passing that?
Good question. So why are we doing this? So we said we want to compute. In the example we saw we were computing marginals.
If we wanted to just marginalize
Yeah.
the first of the
Yeah.
why
Yeah.
are we giving that?
Good question. So here, if you only do pass forward, then you get the marginal p of x3 is what you would get. So forget about the right graph. You're not passing backward. Let's say you're passing messages from x1 and x2 all the way to x3. Then you would get the marginal for x3. Okay. But I was just going to comment that's related to this. If you want to also get the marginals for x1 and x2, you just pass back messages. Okay. If you pass back, then you get a marginal for x4 as well and x1 as well. Sorry, not just x1 and x4. You also get a marginal for x2. Okay. So in 2 passes, a forward pass and a backward pass will give you marginal distributions for every variable node in your graph. Okay. That's like an efficiency gain. Think of if you were doing variable elimination. Okay. You would have to do. Naively speaking, you would do 4 summations. Okay, there are 4 variables here. You would do 4 summations to get 4 marginals. Here, there's some efficiency gain here, in addition to ordering issue. So there's a variable elimination has the ordering issue, but here you're getting with 2 passes of messages, forward pass and backward pass. You're getting all the marginals for all the nodes. Okay. Any other question? Okay. Yeah, so as I said, the marginal is just the, okay, so how do we compute the marginal? So once you have messages from any any bunch of factor nodes, that itself is the marginal, okay? I mean, after you did the 2-pass thing, as I said in the previous slide, then you would have all the, in this case there will be an incoming message, that message itself is a marginal. In this case, so for example, think of x2, it has all its incoming messages, so it got its incoming message from this part, it's got 2 incoming messages from this part, so multiply all those 3 together, would give you the marginal for the x2, okay? Is that clear? Okay, so there is some efficiency gains to be had, and that's why we are looking at this general algorithm. Okay, it's just a clever way to do summations, basically, if you want to summarize it as a concept. And yeah, so I think I'm pretty much wrapping up belief propagation. So this is a belief propagation, and why are we calling it belief? Okay, I'm telling it to you now. Is beliefs are just another words for distributions, density functions, and you know that these messages are essentially like beliefs. Okay, they are some sort of I mean, eventually the messages essentially become probability mass functions. So marginals are just products of messages, right? And distributions, another name for distributions is beliefs. Okay, so that's why it's called belief propagation. Propagation is sending back and forth these beliefs or messages. Okay. Now we only saw three factor graphs. For general factor graphs, there's going to be some circular logic here, because you want to pass a message to one target node, and that message, the target node will compute something locally and pass something else to another node, and then maybe that message is again computed back to you. So there is some dynamics going on, okay, some circular logic. But it will give you wrong answers, but the question is, I mean, it's shown that for some graphs it will not give you the right answers. But you can still use it, and people, in fact, the image segmentation example I was talking about, you have a pixel which is a variable node, and each pixel is connected to other pixels, right? So there is going to be loops, okay? There is going to be, it's not going to be a tree. That image segmentation task, the factor graph is not a tree, okay? And so people apply belief propagation to such a graph, and for that they'll just call it loopy belief propagation, okay? It's just the same algorithm applied on a graph which is not a tree. It's called loopy belief propagation, okay? And it works, and it's an efficient way to compute, infer what is the foreground, what is the background, or infer which part of the image is what, okay? So those are tasks that you can do. Any questions so far? Yeah. Here?
Where you were showing, yeah. So
yeah.
Could you just explain how the sending back the message, you were able to get the marginal probability for x4?
x4, okay. So the graph there is just this, right? So x, I don't know.
Like for x2, you told it like you're basically the two products that are coming in, and the return you're just taking a summation, like product of all those three.
Yeah. So something like this, right? So in the first pass, I mean, so as I said, from what is the message from a variable node to a factor node? It's 1. Okay, there's no message here. Actually, the message. Let's not do that. So let's say we're going. X3 was designated root node. Okay, so I want to pass all the messages to this root node. For a tree graph, there's only one path. Okay, there's not going to be multiple paths. So first message is all going to be all 1. So let's say all these are binary random variables. So first message is going to be like this. Okay, 1 1. Now from here to here, I just said the message from a factor node to a variable is just the incoming message, which is 1, so it's irrelevant. It's just so the message here is just going to be, I don't know what was that. There was no name. So let's say this was a function of x2 and x4, right? Times 1. That was a sum, and then sum over x4 value. Okay. So this is now a function of let's call it g of x2. So this is a message which is being passed to x2. Okay, that depends on that factor function here, right? So this is clear. So this is same thing. So this same thing is happening here and here, right? Those are the two messages passing to x2. Okay, so now x2 got the message, 2 messages from 2 factor nodes, just multiplies them. Let's call it GA and GB. Let's say this is GB of x2. So GA and GB just multiply element wise and pass it forward to this factor node. Okay, now this factor node got one message from other guys. It multiplies that message with its local function, which is a function of x2 and x3, right? Sums over x2 and pass a message to x3. Okay, so that's fine. So this guy got a message, right? I mean, the actual notation is mu of let's call this f prime or something, f prime to x3 of x3. Okay, that's the notation, but doesn't matter. So x3 now got the message. Now you're done. So now you have a bunch of messages. Keep them. Don't forget them. Now I'm saying is pass messages back. Okay, from the root to the leaves. So what is the message from this node to the factor node? It's again 1. All ones. Okay, and from this factor node to from this factor node to x2, you know what the message is. It's very similar to GA, for example, right? It's basically that function f prime just sum over x3, then you'll get some message. Okay, now that message, let's call it GC. Okay, GC of x2. Okay, because it's a message to x2, so it has to be a function of x2. So now at x2 you have all the 3 messages. Okay, so you know what. So the marginal at x2 is just the product of those 3 messages. Okay, that's not the question you asked, but that's fine. So x2 is fine. Now from x2 it has messages from GB and GC. It can find a message from x2 to the factor f. Okay, so that's going to be a new computation. That's going to be a new computation, right? Because I need to multiply GB and GC together element wise, and that's going to give me a message which I can pass to f2. Okay, and from f2 again I have to do that. Not f2. This f. Okay, I got a message, incoming message. That message times this sum over x2 would give me x4, a message to x4. Now that message to x4 is the marginal for x4. Is the claim. I mean, here we are not really doing any proof to say that is the marginal, but that's the procedure. Okay.
Yeah, I get it now. I was getting confused. I thought the message that x3 receives somehow is sent back. So that
no. I mean, so message. So between a factor node and a variable node, a message going in one direction is not going to be using the immediate computation of the message going from the other direction. There are going to be 2 messages, right? I mean, it will not use. It has to use the messages of other nodes getting into it to send a message to a target node. It's not going to use the message from the target node to you send it back to the target node. Okay. Yeah. So where are we? What's the time? Okay. So let's take a 7-minute break and resume at 7:30. We'll talk about more, I guess, a relatively more exciting thing, which is about sampling and give sampling.